What does it mean to be alive? How do we quantify life? A good place to start is with ourselves. We can all surely agree that humans are an example of a living thing. Unfortunately, for the sake of answering the question, humans have a number of qualities that few other things we might agree are alive do not possess. Something like linguistic communication or the use of tools isn't helpful for this discussion. Other characteristics that might seem to qualify life are similarly useless. Perhaps breathing is a prerequisite. However, animals like insects don't have lungs the way most other animals do. So, that similarly is not helpful. Even further, I think we could all agree that something like a rock is not alive. So, what criteria can we use to establish what is and isn't alive? It would be an undeniably monumental task to go through all things on Earth or beyond and decide individually what is and isn't life. So, let's delegate instead. Tasks too complicated or time-consuming for a human can usually be programmed for a computer to handle. This programming comes in the form of a set of instructions that follow a set of rules called an algorithm. Our goal is to create the algorithm that we'll use to determine if something is alive or not. To create a computer program, we're going to have to think like computer scientists. For this to be viable, we must understand what computers can and cannot do. A computer will not simply be able to determine yes or no when presented with an animal or something like one. Instead, computers perform calculations according to their programming using data stored as variables to complete tasks statically or dynamically. For our purposes, we'll need a dynamic program, that is, one that accepts any input and performs the calculations. We don't hard code in any data. A dynamic algorithm will not be difficult to produce, but obtaining the data dynamically would be challenging. So for the sake of time in the argument, we'll say that we have a machine that observes an object and stores information about it for our program to use. What information do we need to know? There's debate as to exactly what it means to be alive. Anyone claiming to have a definitive answer is probably kidding themselves. That being said, different scientific disciplines have definitions for life that can help guide us along and give us helpful information as we gather the data we need to build our algorithm. From a strictly physics point of view, we could describe something as alive if it's a self-reproducing, organized thermodynamic system. While this is helpful and a valid description of what life technically is, it may not be the most helpful definition for our computer. At this point, biology actually becomes very helpful. Biologists have a standard, rigid checklist for what makes something qualify for life. This can come in very helpful for constructing an algorithm, as we can have the computer go through the items and process digitally what fits and what doesn't fit into our definition. The list is composed of 7 characteristics that all living things share. The first item on the list is homeostasis. This is an organism's ability to regulate its own self-contained environment. It keeps itself at a constant state. Secondly, living organisms are composed of an organization of cells. Third, living things all have metabolisms. That is, they take energy in some form and make cellular parts with it. Fourth is that living things grow. Their size increases proportionally. Fifth, living things adapt through heredity. They change in response to their environment by changing their traits over time. Sixth, they respond to stimuli in their environment, most often characterized by the act of movement. And finally, seventh, living things reproduce. Whether sexually or asexually, living things can produce new organisms. Now, how do we take this abstract list and turn it into an algorithm for our computer program? If we were actually writing the program, we could start by setting up 7 Boolean variables, A Boolean value is a binary value. That is, it exists in only one of two states. It can be true or false, 1 or 0. It cannot take on any other value. Let's call our variables homeostatic, cellular, metabolic, growing, adaptive, responsive, and reproductive. Our program is going to use these variables to store information about whatever object we place into our analysis machine. The machine will observe whatever we put into it. Let's say it's Alec Baldwin, and go through assigning a Boolean value to each of the variables. If Alec Baldwin displays whatever quality we're looking for, the machine will tell the computer to assign a value of true to the respective variable. If by some chance Alec Baldwin doesn't display one of these characteristics, it'll be marked as false. When we've had the computer execute these instructions, we can move on to categorizing whether something is alive or not. We can tell the computer to look at each variable where we've stored information about Alec Baldwin. It'll go through one by one and verify that each value is indeed true. In the case of Alec Baldwin, we'll find that each variable is, in fact, set to true. Therefore, we can approve this object and store it. There are lots of memory structures that computers use to store data, but for the sake of time in this example, let's take the array. The array will be the storage type we use, and it will contain all the positive results of our algorithm. Let's say we feed our algorithm an object like a piece of leather. Though the cells are dead, leather is made of an organization of cells. This variable will be marked true. That being said, leather is clearly not alive, and the other variables will be marked as false. In the interest of efficiency, we can actually use this information to make the program faster, because if we want to analyze all the objects we possibly can, we're going to end up with a lot of data. Thus, efficiency is very important when it comes to processing it. We can improve the speed by immediately discarding an object when any variable equates to false. This means that as soon as one characteristic of life is not met in the scan of an object, we do not add that object to the array, and we release the object, moving on to the next one. Though, with one object this won't be significantly faster, over the long run it's going to improve the algorithm's speed. It's certainly possible to optimize this algorithm even further. If we were tasked with actually implementing this, improving efficiency would be a main goal. However, for the sake of this presentation, we're going to say that what we're at is efficient enough. From here, let's take our algorithm and make it more human readable. It's good that we have something the computer can understand, but let's translate it to a flowchart so that we can understand in more plain, simple language exactly what's going on here. Here we have a plain English representation of what our algorithm is actually doing. Up at the top, we have our first step, which is to load our object. That is, we take our machine, we put whatever it is into it that we want to check if it's alive, and it's going to analyze all those variables we talked about earlier. It'll look at it and it'll decide if it displays whatever property we're looking for. That's the next step. It goes through, and one by one, the algorithm, or the machine rather, is going to check, is this or is this not true about each category that we've decided is a qualifier for life. And over on the left, if any of those equate to false, then we're going to immediately discard that object. Anything that goes through and doesn't display all 7 is not going to be an object that we consider alive for the purposes of this program. Over on the right, we'll see that if you end up checking all 7 variables as true, we're going to approve the object. It is alive. At the end of the day, what we have is a relatively compact and simple seeming algorithm that explains how we're going to determine whether something is alive or not. Most algorithms used in computer programming are deceptively simple. They can become much more complicated and mathematical when you introduce measures to improve efficiency. However, for our sake, we're not going to be too concerned with the efficiency of this program, since it's only a demonstration for this presentation. And there we have it. This incredibly simple, small algorithm is going to be what tells our computer exactly how to determine if input is, in fact, alive.